Today's video is on stoichiometry, and so today's learning target is to learn how to calculate amounts in moles of reactants and products by stoichiometric proportions in a balanced chemical reaction. So we're looking at a reaction and determining and calculating the amounts of reactants and products based on their mole ratio. So what is stoichiometry as an introduction? Stoichiometry, stoich means element, ometry is a measurement of, just like geometry, trigonometry. Those are measurements of different shapes or angles. So let's go ahead, and stoichiometry is a measurement of the element and the amounts of the element. So the technical definition for stoichiometry is a mass relationship between reactants and products in a balanced chemical reaction. We use a mole ratio, or also called molar ratio, between different substances in the reactants and products to calculate the amounts of those reactants and products using the balance equation. Mole ratio is basically a proportional relationship, which is a conversion factor in units of moles between reactants and products based on the balanced chemical reaction. So we need a balanced chemical reaction to do stoichiometry. Another way to think of stoichiometry is what you see here, where you see a relationship between bodies and tires and cars. For every one body, you need 4 tires to produce 1 car. If you have 8 bodies, car bodies, you need 4 times that, which is 32 tires to form 8 cars in the end. So if I'm given, so here you have a scenario where you're given 120 tires. So the question is, how many car bodies would you need for that? So it's 1 to 4 relationship, or 4 to 1. For every 4 tires, you would need 1 body. So if you have 120 tires, you would divide this by 4, and that will give you the number of car bodies. So this divided by 120 divided by 4 will give you 30 car bodies that you would need in order to account for the 120 tires. So how many cars would you be able to make out of that? So if you've got 30 car bodies and 120 tires, the ratio relationship, the easier ratio relationship, is between the bodies and the cars. For every 1 body, there's 1 car that's produced. So if you have 30 car bodies, that would be 30 cars. So this idea of stoichiometry is using this ratio here to determine any scenario of given amounts of either cars, bodies, or tires, and we use that ratio to determine any given amount that you're given here, okay? And we proportion it out. Always will this ratio fit the actual balanced recipe or ratio that is in the equation, okay? So let's bring it to a conceptual understanding of what stoichiometry is in chemistry. So if you have a reaction like this, the ratio, the mole ratio between the nitrogen gas to hydrogen gas to ammonia is a 1 to 3 to 2 mole ratio. So again, the mole ratio among all of these substances is a 1 to 3 to 2 mole ratio, okay? So keep that in mind, that we're looking at a mole ratio, not a gram ratio. It is a mole ratio. So here we have 2 moles given to us of the nitrogen gas. To fit this ratio, let's work off of these nitrogen and hydrogen. It's a 1 to 3 ratio. So to figure out how much hydrogen, you just take 3 times the amount of nitrogen. So 3 times this amount is 6 moles. Now we have a scenario where you're looking at the given, which is 2 moles of nitrogen and the amount of ammonia that's missing here. It's a 1-to-2 ratio. 1 here for every 1 mole of nitrogen, there's 2 moles of ammonia that's produced. So 2 moles, you produce twice that, which is 4 moles of ammonia. And then we go to the next scenario. So here in a different example, you've got 4 moles of ammonia. And the easier ratio to work off of is this 2-to-1. So sometimes you kind of work with a different ratio so that you can easily obtain the other ratio. This ratio of 3-to-2 is really difficult to kind of conceptualize. So it's good to work off of these two here. So you're looking at for every 1 nitrogen, there's 2 ammonia molecules. So here you have 4, so it'd be half that. Half that would be 2 moles. So notice this ratio is still a 1-to-2, just like the mole ratio in the balanced equation. To get this number, this is 3 times this amount. So 3 times this amount, just like a 3-to-1 ratio, 3 times this amount is in fact 6 moles. Now we go to the next one. This is a little harder. It kind of progressively gets harder as you go along. So if you have 3.9 moles of hydrogen, a third of that will be how much you would need of the nitrogen. So what's a third of this value? So take this number, made it easy to divide by 3. A third of that value is 1.3 moles. How much ammonia is produced is twice that. So twice that value is how much ammonia. So 2.6 moles is what you're looking at. Now, again, if you want, you can actually go directly between these two. But what you'd have to understand is the ratio is a 2-to-3 ratio. So you take 2/3 of this value to get this value. Okay, a 2-to-3 ratio. So you make it into a fraction, which is 2/3, and that will multiply times this value. That will give you 2.6 moles of ammonia. Now looking at this next problem, you'll notice that you don't have moles. And so you have to do a conversion. And the conversion is from 56 grams of nitrogen, and you must convert it to moles. So you do a side conversion where you take the grams of nitrogen and convert it to moles of nitrogen. And so to substitute those numbers in 1 mole of nitrogen, how much mass is there? 28.02 grams. So you divide these two numbers and then you will get the moles. If you notice the units working out so that you get the mole unit. So the moles of nitrogen with the sig figs is in fact going to be 2.0 moles. So it looks like it's 2 moles, okay? Given the molar mass is 28 and you have 56 grams. So dividing these 2 moles. I like to write it into this equation or into the box so I can see, again, the mole ratio relationship. If I have 2 moles here, I know that I'm going to have 3 times that amount, 1-to-3, 3 times that amount, so it's going to be, 3 times that amount will be 6.0 moles. And then here you have twice. So it's a 1-to-2 ratio, 1-to-2 ratio, so you're going to need twice of what you have here. So if you have 2 moles here, 2.0, you're going to make 4.0 moles. Okay? So here's the conceptual understanding of what a mole is in stoichiometry, or the mole relation in a balanced chemical equation in what is called stoichiometry. So let's look at where we're taking, instead of doing it conceptually, we're using dimensional analysis, which is a mathematical approach to proving or to showing the work for these stoichiometry problems. So here we have an equation, and the equation's all balanced for us. So let's look at the mole ratio really quick. The mole ratio between each of these different substances is the following. For every 4 moles of iron, there requires 3 moles of tin 2 or tin 4 nitrate to form 4 moles of iron 3 nitrate and 3 moles of tin. Okay, so let's go ahead and begin by setting up this problem with the given. If you look at this problem, you'll notice the given is 168 grams of iron. So this is your given. And you want to convert it to moles of tin. Okay, so those are your 2 units that you're trying to get to. Notice you're going from iron to tin. To go from iron to tin, you look at this equation. That means you have to go through this ratio, this mole ratio. So iron to tin is a mole ratio of 3 to 4. 3 to 4. For every 3 moles of iron or tin, you need 4 moles of iron. Okay, so you start off with your given 168 grams of iron. You want to convert that iron into moles first. You don't want to leave it in grams, because to do this mole ratio, you must convert it to mole units. So I'm going to set up my units first, class. I've always emphasized units first, because this is called dimensional analysis. So you're focused on units when you look at dimensional analysis. So moles of iron on the bottom. You always are cross-canceling units, so you always know what the denominator of the next conversion factor will be. And then you want to convert it to moles of tin. This is a mole-to-mole ratio called mole ratio right here. So we can anticipate to go to this period or the balance equation to get this mole ratio. And then you stop here. Sorry. You stop here because you've got your moles of tin. Always focus on what you're trying to find, which is moles of tin. So I'm going to put equal here. So let's go ahead and plug numbers in. In 1 mole of iron, what is its mass? What's the mass of one mole? So it's 55. Looking at the periodic table, it's 55.85. What's the mole ratio between tin and iron? For every 3 moles of tin, there are 4 moles of iron. So notice the units canceling out really nicely with even the labeling of the same substance as they cross-cancel, and you're left with moles of tin. Now, if it's hard for you to think of the calculations, I would put a 1 down here and just multiply the numerator first. When you multiply the numerator, you get 504 top, and then you multiply the denominator, and you'll get 223.4, and then divide those 2 numbers. When you divide those 2 numbers, you get 2.26 moles of tin. Just like our answer right here. Answers are all highlighted in yellow. So going to the next problem. In this next problem, we're looking at 112 grams of iron. And you're trying to get to, so let me underline it just to know that where I'm trying to go. So I'm going from grams of iron to grams of tin. So I first have to convert from tin to iron, I need to use a mole ratio, which means I have to convert my grams of iron into moles of iron. And then I'm going to use my mole ratio to convert from iron to tin. And then I'm going to take my moles of tin and convert it to grams of tin. Let's plug in numbers now. In plugging in numbers, we know that a mole of iron has 55.85 grams. We know the mole ratio between tin and iron. The mole ratio is a 3 to 4 mole ratio. We know the molar mass of tin, because it's the mass in 1 mole, is found on the periodic table, and it's 118.71 grams. Multiply it all through, cross-cancel units, do the math, multiply the numerator, and then the denominator, and you'll get some long numbers here. So bear with me in writing this number out. I'm going to write it in a smaller pen so that we have room. So you'll get 223.4 on the bottom, and then this really long number, 39,800 886.56 on the top. And when you divide those two numbers, you'll get the answer, which is 179 grams of tin. Okay, so these are the two problems to start. Now let's look at the second example. In the second example, you're looking at these ratios can be very intimidating. So that's why using dimensional analysis is really the perfect way to be able to map out how you're working through these calculations. They're very intimidating, especially if you have to do these two substances where the mole ratio is 5 to 8. So that's why dimensional analysis is very nice. So you start off with 32 grams. Here's your given, and here's what you're trying to get to, which is grams of carbon dioxide. So in 32 grams of oxygen, grams of oxygen, moles of oxygen. I need to now convert it to another substance, which is carbon dioxide. And the only way to do it is to go through moles. And that's why I know to do a mole-to-mole ratio between carbon dioxide and oxygen. Notice how the moles of oxygen cancel out. And then you're going to do a last step of converting it from moles of carbon dioxide to grams of carbon dioxide. Now we're ready to put numbers in. 1 mole of oxygen has 32.00 grams. The mole ratio between carbon dioxide and oxygen is a 5 to 8 ratio. For every 5 moles of carbon dioxide, there are 8 moles of oxygen needed. So then we look at this, and this is a gram to mole, so it's molar mass. So there's 44.01 grams in 1 mole of carbon dioxide. You multiply this out, again, because of room, we'll write it in a pen rather than a marker. And so the answer ends up being 7041.6 when you multiply the top. And then when you multiply the bottom denominators, you get 256. And so when you divide these two numbers, you now get 27.5 grams of oh, I'm so sorry. I might have written that wrong. Yeah, no, sorry. 27.5 grams of carbon dioxide. Okay. You should be pausing the video or rewinding if you need to see something else, or see it a little slower or see it again, okay? So the next problem, you're given this substance, which is called pentane, and you want to convert it to moles of water. So focus on the units, moles of water, okay? So notice how it's two different substances, which means we're going to have to do a mole ratio. To do a mole ratio means to convert my beginning units into mole units if it's in grams, like it is now. So here's my starting units, and I want to convert it into grams. So grams on the bottom, moles on the top. Units setting up, moles of pentane on the bottom, moles of water on the top. And we stop there. Why? Because we're asked to find moles of water. So we can, if you look at the cancellation of the units, grams of methane or pentane cancel out. Moles of pentane also cancel out, and so you're left with moles of water. So now let's substitute values in. For every 1 mole of pentane, there are 72.17 grams. And we found this from the periodic table. It's called molar mass. And then here you see a mole-to-mole ratio between two different substances. So we know to look at the balance equation to look at the mole ratio between water, which is 6 moles, and pentane, which is 1 mole. So multiply that out. We'll have a little room here. So the top numbers multiplied out is 864. Bottom numbers is still 72.17. Divide those two numbers together, and you get an answer that's 11.998 or something like that. And you round it to 3 sig figs. And when you round it to 3 sig figs, it rolls over to become 12.0 moles of water. Hope this helps.